Hello and welcome to this talk about the connectivity augmentation problem. My name is Vera Traub and I will present some joint work together with Federica Cecchetto and Rico Zanclusen. Let me start by introducing the connectivity augmentation problem. In this problem, we are given a k-edge connected graph, as you can see here in an example in black here, and we are also given an extra set of edges. These are the red edges here, and we'll also call these red edges the links in order to distinguish them from the edges of the graph G. And now in connectivity augmentation, our goal is to increase the edge connectivity of the graph G by 1 unit. This means we want to obtain a k+1 edge connected graph by adding as few links as possible to the graph G. Or in other words, I can also say we want to cover all the minimum cuts of the graph G using as few links as possible. Now it is well known that the connectivity augmentation problem reduces to the special case that's called cactus augmentation. And the cactus augmentation is simply a special case of connectivity augmentation where k equals 2 and G is a cactus. So this means that in the graph G, every edge is contained in a unique cycle. So this reduction here is also approximation preserving. So if we're interested in approximation algorithms for the connectivity augmentation problem, we may assume that k equals 2 and G is a cactus. Another important special case is the tree augmentation problem, and it's known that if k is odd, then connectivity augmentation reduces to tree augmentation, and tree augmentation, or also in short TAP, is simply the special case where k equals 1 and G is the tree. So now what is known about these problems in terms of approximation algorithms? So there are many classic and quite general algorithms for much more general network design problems, for example, like methods like primal dual algorithms or Jane's iterative rounding method. And these kind of algorithms, they all yield a true approximation, both for tree augmentation and for the more general connectivity augmentation problem. Now for tree augmentation, there has been a huge amount of work and also a lot of progress regarding approximation algorithms with the ratio better than 2. And so the best previously known approximation ratio is a 1.458 approximation. And this is basically comes from combining these 3 papers here that are marked in green here in this list. And however, despite that much progress for the tree augmentation problem, this progress didn't transfer to the connectivity augmentation problem so far. And in fact, only at last year's STOC, there was the first paper by Birker, Grandoni, and Emily that achieved an approximation ratio of better than 2 for the more general connectivity augmentation problem. And this 1.91 approximation here is based on an elegant reduction to the Steiner tree problem, but it uses kind of completely different techniques than those that were used for TAP before. And so what we do in our paper here is basically we present some new methods that allow for applying these methods developed for TAP, also for the more general connectivity augmentation problem, and then we also strengthen these methods, and altogether we obtain a 1.393 approximation algorithm for the connectivity augmentation problem. So this means even for the more general connectivity augmentation problem, we achieve an approximation ratio that is below what was known for the special case TAP before. So this is the result I want to talk about today, and let me first give you a brief overview of our approach. So our approach has several main components, and the first step of our algorithm is a reduction to a very special structured type of instances, so-called k-wide instances. In order to explain what k-wide instances are, let me first introduce the notion of terminals. So terminal in a cactus is simply a vertex of degree 2. And you should think of the terminals in a cactus sort of as the analog of the leaves in a tree. And now what is a k-wide instance? So in a k-wide instance, there exists some center, some vertex like this green one here, such that if we look at each of these subcacti that are hanging off the center, then each of these subcacti contains at most k terminals. So in this example here, I have 3 different subcacti hanging off the center, and each of them contains at most 5 terminals, so the instance is 5 wide. And now what we show in our as a first step in our paper is that if we have an alpha approximation algorithm for k-wide instances for any constant k, then we have an alpha plus epsilon approximation algorithm for the general cactus augmentation problem, and thus for the general connectivity augmentation problem. Now then the second component of our approach are the so-called backbone procedures. these are two algorithms for k-weight instances that have different kind of approximation guarantees depending on what type of links an optimal solution uses. And so here we distinguish between in-links. These are links that are simply within one principal subcactus hanging off the center of the instance, and cross-links that go between different principal subcacti hanging off the center. And so the backbone procedure A here is good if opt uses many in-links, while the second backbone procedure is good if opt uses many cross-links. And now you may notice that here I write something about costs, and in fact it is true that these backbone procedures for k-weight instances also apply to the weighted setting where the links have cost. And the reason why the whole approach works only for the unweighted instances is because this reduction to k-weight instances breaks if we introduce weights. And now returning simply the results of better of the two backbone procedures would already yield as we have approximation algorithm for k-weight instances, and this is we have the Zepson approximation algorithm for general connectivity augmentation. This would already be a significant improvement of the previously known approximation guarantee for connectivity augmentation, but it's not quite as strong as what I claimed in our main result. So we also need a third component here, and this is what we call stack analysis. And this is basically a strengthening of this backbone procedure A here. Good. So this is an overview of the different ingredients that we need to prove our main result. So let me get in the following into a little bit more detail of what happens inside these three green blocks here. And let's start with the reduction to k-weight instances. Okay, so to prove this reduction to k-weight instances, we use the well-known round-cut procedure that you might have seen also in the context of approximation algorithms for very different type of problems. And so let me briefly explain how this works. So in this round-cut procedure, we always have a fractional solution. This is current point x, where we have variable xl for every link in our instance that tells us to which fractional amount we take this link. And then we will give that current fractional solution into a rounding algorithm that we still need to design. And either this rounding algorithm succeeds and rounds this fractional point to a good solution of our cactus augmentation instance, or the rounding algorithm might also fail, but then it has to return a separating hyperplane. This is some hyperplane that separates our fractional point x here from the convex hull of optimal solutions of cactus augmentation. And if we get to the separating hyperplane, we can simply plug this into the ellipsoid method and do one iteration of the ellipsoid method. This will give us a new current point x that we can then again give it into our rounding algorithm. And because the ellipsoid method will terminate after a polynomial number of steps, and at some point our rounding algorithm will succeed and will output as a good solution of the cactus augmentation instance. Good. So this is the round-cut framework, and the main part of the work is designing this rounding algorithm that, given a fractional solution, either rounds it to a good cactus augmentation solution or returns a separating hyperplane. Okay, so the main idea of our rounding algorithm is as follows. So remember that we want to reduce to k-weight instances, so we assume that we have a given alpha approximation algorithm for k-weight instances. So the general high-level idea is that given our instance of cactus augmentation, we want to split this into many k-weight instances, then apply the alpha approximation algorithm to each of these k-weight instances, and then somehow merge these solutions to an overall solution of the original instance. And so let me now start by explaining you what I mean by splitting an instance. You can see an example also to split here in the picture on the left. So I look at some instance of the cactus augmentation problem, and now I want to split this instance here at some cut, this cut C here, which will always be one of the min cuts of the cactus, so a cut that contains exactly two edges of the cactus. And now splitting the instance at this cut C here simply means that I split it into this left and the right instance here, where the left instance arises from the original instance by contracting everything that's on the right side of the cut C, and the right instance here is obtained from the original instance by contracting everything that's on the left side of the cut C. And so this splits our instance of cactus augmentation into two smaller instances of cactus augmentation, and it also splits our fractional point x into two fractal points for these two instances that I obtain here by splitting. Now ideally I would like that the values, so total x load of these the fractional solutions for these two instances that result here from splitting, so from the left and the right instance, add up to the LP value, so the total X load on the links of the original instance. However, this is not quite true, unfortunately, because the links that are crossing the cut C here, they appear both in the left and the right splitted instance. So the links that are contained in the cut C, they somehow double, and also the X value on these doubles because it appears both in the left and the right instance. And in order to control the increase of the total fractional X load on the links, we will make sure that we split only at cut C where that are what we call light. So we'll only split at light cuts. These are cuts where the X value crossing the cut is low. So that means bounded by some constant. And we will in the following also make sure that we do not split the instance too often, so that we can somehow increase the cost increase that we get by splitting the instance repeatedly. So this is the splitting operation that we have. Now, ideally, we would like to apply our alpha approximation algorithm for k-wide instances to each of the instances that result from splitting the instance. And so maybe this algorithm, then we computed some red solution F1 here for the left instance and some orange solution F2 here for the right instance. And now, of course, we want to merge these solutions to a solution of the original instance. And a natural thing to do here is would be to just kind of undo the contraction here, so kind of mapping things back to the original instance, and just take the union of the two solutions, F1 and F2. Now, unfortunately, this is not a feasible solution to the cactus augmentation instance that we had at the beginning. So this kind of strategy, indeed, it worked for tab, but it doesn't work for cactus augmentation anymore, because you can see here there's this one green cut, for example, that is not covered after merging, so after simply taking the union of the red and the orange solution. Good. So what we have to do is we'll have to add some extra set of edges, like this blue edge here, that repairs this cut and covers the remaining cuts that are still uncovered. And of course, we somehow need to control the number of blue links that we need to add here. And so the key lemma that we prove here is that we show that we can find a solution F. So a set F of links here, such that F1, F2, and F together are indeed a feasible solution. So we can find a set F of links that completes the union of F1 and F2 to a feasible solution of the overall instance. And the number of blue links that we need to add here is bounded by the number of red links that are contained in this cut C here. So this means we can somehow control the number of blue links here, but our upper bound depends on the number of red links in this cut C here. So we better don't compute just any cheap red solution here, but we would like to have one that is cheaply mergeable, so one that has only few edges in this cut C here. And in order to obtain this property, we show the following lemma. So remember that the cuts that we split are always light, and then we show that if the cut C is light, we can either find a cheaply mergeable alpha plus epsilon approximation F1. So cheaply mergeable here simply means that red has fewer links in the cut C, or we can find a separating hyperplane. And the intuition behind this is that if the cut C is light, that somehow suggests that means that the LP kind of suggests that there should be a good solution that has only few edges here in this cut here. So either we can find such a good solution F1, or we can find in a hyperplane that separates our fractal solution from the convex hull of optimum solutions. So these are the ingredients that allow us to merge our solutions to a solution of the overall instance at the end. Okay, so now we discussed like what splitting and merging means. And now it turns out that if in our instance it happens that all the cuts are light, then we can indeed, using the splitting and merging operations, decompose our original instance into k-wide instances, and we'll of course only split at light cuts, and we can also make sure that we do not split too often. However, of course, it might happen that maybe there are a lot of heavy cuts in our instance, and remember, we never want to split at heavy cuts, so we might be in trouble, and maybe we cannot decompose into k-wide instances. And to handle this, we have an additional step, which means that namely the step first reduces to an instance where we have only light cuts. And in order to reduce to this light cuts only case, we show that we can find what we call a heavy cut covering. Namely, we can find a set H of links such that every heavy cut, so every cut that is not light, is covered by this set of links. And the total number of links that we need is only an epsilon fraction of the total LP value, so of the total number of links that our fractal solution suggests that we use. And finding such heavy cut coverings have already been used, like in the tree augmentation setting, and there it was kind of easy to find these heavy cut coverings. In connectivity augmentation, this turns out to be a bit harder, and so what we do here is that we, in order to find these heavy cut coverings, we reduce this problem of finding these heavy cut coverings to a special type of rectangle hitting problem. And then we show that for these rectangle hitting problems, we can find an LP-based constant factor approximation, which we can then in turn use again to find this heavy cut covering. Good. So these are the components that we needed for our rounding algorithm. So let me summarize briefly what we do here. So the first step is we reduce to the setting of light cuts only. That's where we use this connection to this special type of rectangle hitting problem. Then we split our instance into k-wide instances. For each of the k-wide instances, we either find a cheaply mergeable solution or a separating hyperplane. And then in the end, we merge all these solutions to a solution of the overall instance, or if for one of these instances, we didn't find a good cheaply mergeable solution, it will return a separating hyperplane. And this whole rounding algorithm is then used in the round or cut procedure, and this gives us this reduction to k-wide instances. Okay, so we are now in the setting where we have k-wide instances. So the next step is we want to find these backbone procedures for k-wide instances. And remember that these backbone procedures, these were two algorithms. One algorithm is the in-link algorithm that computes a solution that is good if there are many in-links, so many links inside one of these principal subcharacteri hanging off the center. And there is the cross-link algorithm that computes a solution that is good if there are many cross-links, so many of these red links here that are between different principal subcharacteri hanging off the center. And note that the better of the two solutions of the in-link algorithm and the cross-link algorithm already gives us as we have approximation for k-wide instances. So let me start by explaining the in-link algorithm. This is actually the simple one. So the more interesting and more difficult one is the cross-link algorithm. So for the in-link algorithm, we simply look at each of these principal subcharacteri individually, and we just compute an optimal solution for each of these principal subcharacteri. And this is possible because calculus augmentation with a constant number of terminals can be solved efficiently in polynomial time. So here is the point where we exploit that our instance is k-wide. And then so we do this for each of the principal subcharacteri, compute a solution, and in the end we simply return the union of these different solutions for the principal subcharacteri. And this gives us the desired approximation guarantee, basically because the in-links are just contained in one of these principal subcharacteri, while the cross-links interact with two of these, at most two, or basically exactly two of these principal subcharacteri, and that's why we lose a factor 2 on the cross-links here. So that's the in-link algorithm. This is fairly simple. Let's go to the cross-link algorithm, where we wanted to, that's the algorithm that should be good if there are many cross-links. And let's first look at the cross-link algorithm that was already known for the tree augmentation problem. And in TAP, so this is a paper by Fiorini et al., they first looked at the following LP relaxation, where we have a variable for every link. And we minimize, of course, the total cost of the links that we use. And we want that every min cut of G should be covered. So there should be the total fractional value crossing this cut should be at least 1. And of course, X should be non-negative. And then Fiorini et al. Strengthened this LP further by adding these so-called zero-hash Schweitzer-Montgomery kits that can be obtained here from basically some strengthening of this LP that can be obtained in somewhat automatic way. It's not particularly important for this talk here what these cuts are exactly. But so what Fiorini et al. Showed is that for TAP, first of all, this LP with these zero-hash Schweitzer-Montgomery kits can be solved in polynomial time. And second, any feasible solution X to this LP here can be rounded to a TAP solution with the desired cost bounds, where we lose a factor 2 on the cost of the in-links, but we lose nothing in the cost of the cross-links when we round. And so the basic idea of our algorithm is to kind of transfer this we want to generalize now this algorithm from TAP to the connectivity augmentation problem. So a natural thing to do is to just look at the very same LP. And the first question that we should ask is, can we actually at all solve this LP in polynomial time? And in fact, I don't know whether we can solve this LP in polynomial time. So this is already the first problem that we run into here. So what we do in order to get around this is we kind of modify this LP a bit. Namely, we don't add all of these zero hash fatal-Montgomery cuts, but we only add these zero hash fatal-Montgomery cuts that can be obtained from a laminar family, some subfamily of the min cuts of G. So we don't look at all zero hash fatal-Montgomery cuts that can be obtained from all the min cuts of G here, but we only look at those that can be obtained for a laminar family. And so the first, and there's some kind of simple observation, is that separating these zero hash fatal-Montgomery cuts that can be derived only from this laminar family here, this reduces to separating these zero hash fatal-Montgomery cuts for a tab instance, and thus by the result of Fiorini et al, this can be done in polynomial time. So this is good. So this means we at least can solve the LP, but of course we have a significantly weaker LP here. We didn't add all the zero hash fatal-Montgomery cuts. But what we can show, and we show in our paper, is that if we choose this laminar family here in the right way, and if we choose this as a very particular laminar family, min cuts of G, then we can still obtain the good rounding result, namely then any feasible LP solution of this LP here can be rounded to a Cactus augmentation solution where we lose at most a factor of 2 in the in-links and nothing in the cross-links. And I really want to highlight here that the main thing here is that you really need to choose this laminar family here in the very right way in order to make this work. So this is kind of where the main magic of this part here happens, is to choose this laminar family in the right way. Good. So this is some brief idea of how these background procedures work. So at the end, let me say a few words about this last part here, the stack analysis. And the main idea of the stack analysis part is we look at some algorithm that's basically a strengthening of this algorithm, of this in-link algorithm, where we simply considered each of these principal subcacti independently on its own. And now we do not just simply compute the best solution for each of these principal subcacti, but the algorithm will now become LP-based. So we start by solving a certain carefully designed LP relaxation. And then for each principal subcacti independently, we sample now a solution from the LP. So just a solution for each of these principal subcacti. We do this for all of them, and we sample this from the LP. And then again, as before, we simply take the union of all of these solutions. And now the only additional step that we have here is that in the end, now it might be that some of the links that we have here, after taking the union, some of them might be redundant. So for example, after taking unions of these solutions here, this red link here becomes redundant, so I can simply remove it from the solution and still maintain a feasible solution. And so in this last step, we simply remove as many crosslinks as possible. So this algorithm is similar to an algorithm by Grandoni, Kalaitis, and Seclusion for tab. So the algorithm here is essentially the same as theirs. Our main contribution here is that we provide a new approach to analyze this algorithm, which leads to a stronger lower bound on the expected number of links that we can remove here in this last step. And this analysis is based on assigning crosslinks to so-called stacks. This is what you can see here in green on the right, and that's why we call our new analysis the stack analysis here. Good. So this is just a few words about this last ingredient here. And overall, I've now given you an overview of this result here, which is a 1.393 approximation algorithm for the connectivity augmentation problem. And let me conclude with some open questions. So the first question I want to mention is, of course, can we improve the approximation guarantee further? So 1.393 is certainly not the right number, and probably even the same algorithm should have a better approximation guarantee. So it'd be nice to find some better analysis for this, or maybe some different techniques that where some different algorithm that leads to a better approximation guarantee here. And another question I want to mention is about the weighted connectivity augmentation problem. So there it's still open whether we can beat the factor 2 at all. And even like for the special case of weighted tree augmentation, we have recently shown together with Rico's inclusion that for the first time we could actually beat the factor 2 for the special case. So for weighted tree augmentation, we recently showed that we can obtain an approximation ratio that is less than 1.7, and that's quite a bit better than 2. And now in this paper here, what I showed you today, we kind of saw that in the unweighted setting, we were able to transfer these techniques and make use of them also in the more general connectivity augmentation problem. And it would be nice to see if similar things can also be done in the weighted setting, and we could this also beat maybe factor 2 for weighted connectivity augmentation. And with this open question, I would like to conclude my talk. So thank you very much for listening.